Hello, people from the future. Welcome to Normalized Nerd. Today I'm very excited because I'm gonna show you not one, but two generative adversarial networks that I have created. Well, the first one will generate English alphabets, and the second one will generate my mother tongue, that is Bangla alphabets. But the most important thing that you will learn from this video is how to train a stable GAN. Trust me, training a GAN is not an easy task. It took me more than 2 days to come up with a stable architecture and a stable set of hyperparameters. And obviously, I had to read and research a lot. So, I'm gonna share what I have learned so that your GAN journey will be a bit smoother. Well, obviously, I can't tell you that you will be able to train a GAN in your first attempt, but what I can surely tell you is it will be much easier for you. If you are new here, then please subscribe this channel and hit the bell icon. I make interesting machine learning and data science videos regularly. So let's get started. First, I'm gonna show you some of the best results that my models have produced, and then I'm gonna show you how I built the models, okay? Well, these are some of the English alphabets that my model has produced, and you can see that these alphabets are very much recognizable. Like here is A, J, P, E, S, T. Let me show you some of the Bangla alphabets. Well, for those who don't know Bangla, let me tell you that Bangla alphabet generation is harder than English alphabet generation. Why? Because Bangla contains more alphabets. Specifically, I have taken here 50 alphabets. This alphabet is known as TH, and this is the output of my model. You can see that how closely it resembles the original form. By the way, this gray and black images are actually written by me, and you can compare here that my handwriting and the model's output are very close. So this gives us the idea that my model can actually generate Bangla alphabets. Now let's jump into the coding section. First, I'm going to show you the dataset. Well, here I am using an MNIST style dataset. That means every image in this dataset is a grayscale image and the dimension is 28 by 28. Currently, you are seeing 100 random images from the dataset, and obviously I'm going to link the dataset in the description, so make sure to check that. Now, before we can use these images in our training, first we need to normalize them. Now, generally, we normalize by dividing the pixel values with 255. That will normalize the values between 0 to 1. But in this case, we normalize the values between -1 to +1. We are doing this because later we want to use the tan-h activation function in the neural networks, okay? Now we are going to build our GAN. Well, I like to build a GAN in 4 steps. The first step is building the generator. Here you are seeing the generator for the English GAN. If you want to know how this thing works, then I would highly recommend you to check my previous video where I have explained the mathematics behind GAN. But in this video, I'm going to show you the implementation only, okay? So the concept is very simple. This generator is a neural network, obviously, and it uses convolution layers. We input a random noise vector to this generator and we hope that it will produce English alphabets. Now for MNIST type datasets, I have seen that it is better to use dense layers as the first few layers. So you can see that the first layer is a dense layer containing 1024 neurons. And you can see that I have used batch normalization here. I'm not going to explain batch normalization here, but understand that it helps us to improve the training time. That means because of the normalization, we will get to the optimal solution much faster. In the second layer, I have again a dense layer. This time the number of neurons is even higher. You can see that in both the cases, I am using activation as ReLU. Well, you can actually use leaky ReLU also. After that, I am reshaping the output. Well, we are doing this because we want to apply convolution afterwards. So I am reshaping the output vector into matrices of 7 by 7, and the number of matrices we will get is 128. How I get this number? Well, just multiply 7 with 128 and you will get 6272. So you can say that I have first decided what I would want as the dimension of my 2D matrices, that is 7 by 7. And according to that, I have chosen the number of neurons in the second dense layer. After that, we are using here upsampling 2D. Why? Remember, we wanna produce images of 28 by 28. But now I only have matrices of dimension 7 by 7. So we need to upsample this. After the upsampling, I'm using convolution layers. Here you can see that I'm taking kernels of 2 cross 2. And as the initializer of the weights, I am taking random numbers from a normal distribution. Why am I doing this? Because it has been seen from many experiments that if we initialize our kernel according to a normal distribution, then it gives us better results. Here also you can see that I am using batch normalization, and here I am using activation function as leaky ReLU. Again, I'm using an upsampling layer, and using this upsampling layer, I will be actually getting to the 28 by 28 dimension, okay? And after this, I'm using the last convolution layer. Here, the number of convolution filters will be equal to the number of channels in our image. As we are using grayscale images that contains only one channel, that's why here channel equal to 1. And here the activation function is tan h. As you saw earlier, I was normalizing the pixel values between -1 to +1, and tan h function ranges between -1 to +1. That's why I am using this. Now notice one thing, that I haven't compiled the generator here. We will do that in the third step, okay? Now comes the step 2, that is building the discriminator. Here is my discriminator, and discriminator is nothing but a binary classifier for image data. So obviously this will also be a convolutional neural network, okay? So in the first layer, I'm using conv2d layer, and the filter size here is 5 cross 5, and the number of filters is 64. Now the input shape will be 28 by 28 by 1, because this neural network will take original data or the data created by our discriminator as its input, okay? And here I am using leaky ReLU activation. In the next layer, I am using the same convolution, but here the number of filters is 128 instead of 64. Then again comes leaky ReLU, and after that I'm flattening the output. Why? Because we want to pass it to a dense layer. Then comes the dense layer with 256 neurons. And at last, I am using a dense layer with just one neuron because it's just a binary classifier, and the activation will be sigmoid. At last, I'm compiling the model with a custom optimizer. Well, the default Adam optimizer will not work here because the learning rate for that is very high with respect to what we are doing. If you just see the code, you will understand what I have chosen as the learning rate. And the loss here will obviously be binary cross entropy. Now, while determining the architecture for discriminator, understand one thing. You want to make your discriminator a bit less powerful than the generator, because in these type of GANs we want the generator to win the battle, so that we can generate data that looks very similar to the original data. And for that we need to fool the discriminator. Now comes our third step, that is combining generator and discriminator. First, let me explain why would you want to combine the generator and discriminator. Well, for training the discriminator, we can train that alone. But for training the generator, we first need to combine generator and discriminator, and then from the output of the discriminator we need to compute the loss and then backpropagate it through the generator. Now the most important thing here is discriminator should not be trained while training generator. So to ensure that, we need to make the discriminator.trainable equal to false, okay? So this is actually very simple. First we are defining the input layer, that is just the shape of our noise that we are going to provide to the generator, and then the generator is producing fake data, and after that the fake data is passed through the discriminator and it will produce some output. And to build the GAN, I'm just using the model class, and in the parameter I have to pass noise and output. So this will tell Keras to make a model in which the first layer is the noise layer, then comes the generator, Then the output of the generator goes to the discriminator, and the discriminator will produce some output based on which we are going to compute the loss, and then we are going to backpropagate. But while the backpropagation, the discriminator is not going to be trained. Only the generated weights will be modified. And you can see here the loss function is binary Carson entropy. Now note that in some experiments it has been found that if we use two different learning rates for two different models, then it performs better. But in my models I have found that if I use the same modified Adam optimizer for both generator and discriminator, it works fine. Now comes the last portion, that is training. Okay, this is the most important part of this video, and I would suggest you to pay your utmost attention here because you will find some techniques which might feel a bit weird at first, okay? So, this is my training loop, and the outer loop is traversing through all the epochs, and the inner loop is traversing through all the batches. Well, steps per epoch is defined by number of samples in our training set divided by batch size. In this case particularly, I am taking 100 epochs and batch size is 128, okay? Okay, so to do the training, first we need some noise, and the noise here is input to the generator, and I am building the noise vector by drawing numbers from a normal distribution. Particularly, this is a standard normal distribution because the mean is 0 and standard deviation is 1. And how many noise vectors should I produce? Just the batch size number of vectors, okay? Then I'm gonna pass this noise to our generator and this will produce the fake data. For this we can use the dot predict method. After that, we need real data also. To do this, I am drawing batch size number of data points from our training data randomly. Then we need to concatenate this real data with the fake data to make a new data, and we are gonna feed this data to our discriminator. Now for training the discriminator, obviously we need some labels, right? First I'm defining a vector of zeros, and how many should I produce? Just 2 times the batch size, because remember we have taken batch size number of fake data and batch size number of real data. Now comes a very weird thing. Well, in normal binary classification, you have seen that we use levels 0 and 1. But here we use a concept called level smoothing. So instead of 1, I am using here 0.9, and instead of 0, I am using here 0.1. So fake data is corresponding to the 0.1 and the real data is corresponding to the 0.9. Now the point is why we are doing that. Well, this is because we don't want our discriminator to be overconfident of its prediction. We know that at first the discriminator will work very well. So just to make it perform a little poorly, we are leveling them like that. Now we are just gonna train the discriminator, and for that we can use the train on batch method, and in the parameter I have to pass the input and the labels. Now we need to train the generator. For that, we need to first define the labels for the generator. Now here is another weird thing. And if you remember my previous video, then I have said that fake data corresponds to the level 0. But here you can see the levels of the generator is just a vector of ones. Well, this is because while training the generator, we are deliberately making the discriminator to perform poorly by giving it the wrong label. We are making the discriminator think that we are passing real data, but in reality, we are passing fake data. And I am once again reminding you that here our target is the generator should outperform the discriminator. And in the next line, you can see that to train the generator, I am using the GAN, as I mentioned in the last section. After that, I am just printing the losses of the discriminator and generator, and at last you will see that I am displaying some of the outputs of my model. While displaying the outputs of the generator, you must use a fixed noise, because in this way only you will find that how the outputs of your generator is changing as the number of epochs is growing for a given input. So now you are ready to train the GAN. How would you know that your GAN is actually training as expected? Well, it's hard to tell because it might happen that your discriminator loss is really low. but your generator loss is continuously increasing. In another case, it might happen that your generator loss is oscillating between two values. Another case might happen that your losses are low, but the outputs of the generator are not really mimicking the original data. Well, here's a rule of thumb. If your discriminator loss is really close to 0 and your generator loss is exceeding 3 or 4, then it is more likely that there's an error in the training. Then you might want to change some hyperparameters. In an ideal training, the discriminator loss should be something around 0.5 and the generator loss should be less than or around 2. Okay, and also display the outputs, because in that way you will know if the generator is actually mimicking the dataset. Now I'm gonna tell a bit more about the Bangla, and after that I will show you the evolution of the outputs of both English and Bangla. Okay, so currently you are seeing 100 random alphabets from the Bangla dataset. Obviously, the link to the dataset will be in the video description. And in the Bangla GAN, pretty much everything is same as the English GAN, but the generator in the Bangla GAN is a bit advanced. Let me show you that. So the first few layers are exactly same as the English GAN, but here I have added one extra convolution layer. This is needed in this case because, as I told you earlier, there are more Bengali alphabets than English. Specifically, I have used these 50 alphabets. Yeah, I have written them. It's not every day that you get to write the Bengali alphabets, do you? And now I'm gonna show you the evolution of the outputs. First, see the evolution of the English GAN. Now see the evolution of the Bangla GAN. Okay, so that was all for this video, guys. I hope you enjoyed this video and learned something. Please share this video and subscribe to my channel. Stay safe and thanks for watching.